So in this activity, we're going to be analyzing data from Fermilab's Tevatron Collider. In 1995, a proton was collided with an antiproton, and this collision resulted in a top quark and an anti-top quark. Now this top and this anti-top pair do not exist for very long. Almost immediately they start to decay. And so we can see in this particular diagram the resulting products. So we have this proton that's coming this way, and we have an antiproton that's coming this way. And we get a collision. And this collision produces this top quark and this anti-top quark. The top quark is going to decay into a bottom quark, and this releases a jet of energy. This also decays into a W boson, which breaks down into a muon and a neutrino, which again, both of these are going to give off energy. The anti-top quark is essentially the same thing. It decays into an anti-bottom quark and a low energy muon, which also releases a jet of energy, and a W boson, which decays into a quark, which releases a jet of energy, and an anti-quark, which releases a jet of energy. And so this gives us a really, really good idea of the different products that come out of this particular event. Now, the universe was extremely kind to us with this event because the decay products essentially exploded in a two-dimensional plane rather than a three-dimensional plane. So when we look at this energy signatures on flat paper, this is really what the explosion looked like. They all went out in this direction. There wasn't a lot of motion in this Z direction, so we don't really have a 3D picture. We only have a 2D picture, which is wonderful. This actually helps us and makes it relatively simple to analyze this event. Now, when we look at this, this is the computer signature of the event. And so you can see those jets of energy. And again, this is all going in this two-dimensional plane. So we're really looking at an accurate representation of the energy directions, and this makes it really simple to analyze. So these signatures include 4 distinct blasts of particles called hadronic jets. And these are just decaying particles jetting out, leaving energy behind. And we can see one here. So this is one of our jets of energy. Here's another jet of energy, and another jet of energy, and another jet of energy. So we have 4 jets of energy that we can pick up using our computer. We also have a solid green line right here, and this is representing the muon track. And if you look closely, there's another dotted green line, and this is hidden here in this lower jet. This is the soft or low energy muon. What we don't see here is the energy from the neutrino. Now, in most cases, neutrinos are not detectable, and their existence is found by looking at the total momentum of the system. Now, the total momentum before the collision is 0, because we have 2 particles, and they are moving in the same velocity with the same mass, but in opposite directions. So our net momentum is 0. That must mean then that the total momentum after the collision is 0 as well. So if we add up all of the momentums of the particles that we can detect, it becomes a pretty simple matter to find the momentum of the neutrino. Now, remember that this is not Newtonian physics. These particles are moving at the speed of light. And because of how we define the speed of light in particle physics, energy, momentum, and mass are all the same value. Mass represents a kind of energy, and motional energy, or kinetic energy, is changed by E equals mc squared. So the jets that we see on our data are showing the energy signatures, but we can also say they represent the momentum or the mass of the particles because all of those values are the same when those particles are moving at the speed of light. So this lets us do a couple things. First, we can determine the energy of the neutrino. To do this, we need to determine the missing momentum of our system. We can use the observable particles to find the vector sum of the jets. So really, this is just a simple conservation of momentum problem, where the momentum of the neutrino is equal to the negative vector sum of the observable particles. Now we can also add the energy numbers to get the total energy of the system, which is also the total mass. This total mass is then the total mass of the top quark and the anti-top quark. So if we divide that total by 2, then we can determine the mass of the top quark. So this just boils down to a vector sum diagram. Now looking at our diagram, we have 6 energies to consider. So let's just start here on our x-axis and work our way around. I'm just going to draw this axis so it's a little bit easier to see. Maybe. My pencil. So there's our x-axis, and let's go ahead and draw our y. This is just to give us a little bit better feel of where our reference plane is. Okay. So this is our x-axis here, and this is our y-axis here. So remember that these are all moving, all of these little particles are moving along our x and our y axis. So our z axis can be pretty much ignored here. So let's move over here to this top jet. This is the first one, and we want to draw this energy signature as a vector. So we need to determine an angle and a magnitude. The magnitude is given at 82.2 giga-electron volts per C. Now this is energy, but remember it also is the value for the mass and the momentum. So we can use that for any of those particular properties. Now we just need the angle. This jet is actually a pretty wide one, so to determine the angle, we're just going to find the middle and measure it from there. So we just are just going to come in. These are all the same size, so we're just going to come in and find the center of that one, and that is going to be our vector for this energy jet. So we're going to draw that here to see it a little bit better. Okay. So this is where our vector is actually going to be going. And so now we need to measure this angle. And if we look at jet 1, let's see, so jet 1, it looks like an angle of about 76. So we have an angle of 76 degrees, and we know that the value for our energy is 82.2 giga-electron volts. So I'm just going to write that over here to the side. But you can't see. Somewhere. There we go. No, it's not straight. Okay. So jet 1, we have an angle of 76 degrees with respect to our x-axis and an energy of 82.2. Now there's also a muon track kind of hidden in here. We've got this green line. So this is another one of our energies that we want to consider. So if we measure this angle here, say maybe this would be 67. So our muon track has an angle of about 67 degrees, and its energy is 34.2 giga-electron volts per C. Now moving around to jet 2 is over here. So we're going to find the center of this one as well. This one happens to be just kind of right on that line. So let's draw that vector, or the path of this vector, not actually the vector itself, and measure the angle. So if we measure this angle, it looks like it's right at 135. So jet 2 has an angle of 135 degrees from our x-axis, and it has an energy of 39.8. And then we just keep going around. So here's our soft muon. So our muon 2. If we measure that angle to be, here it is. Let's see, this is going to be 160, 174, about 174. And it has a very low energy of 8.6 over here. So our third jet is a little bit smaller. They'll have this bracketed. So this jet right here is bracketed through there. So we have a 1 and 2, 1, and then about halfway through this one, is where we want to draw that line. So when we measure that, that one's a little tiny thing. We measure that is going to be around 1, 2, 3 degrees below the X. So this is 180 plus 3. So our jet 3 is 183 degrees, and it has 18.8 energy. And then we just have this one more. And then this is the center, so we're going to draw our line through the center of this. And if we line up our thing here, we've got, let's see, 121, 2. So 180 plus 122 would be 302 degrees. So jet 4 is 302 degrees, and it has an energy of 48.3. All right, so now we have the values and the angles of all of our vectors. So these are momentum vectors that we can describe. And so what we're going to now is create a vector diagram. I'm a big fan of graph paper. So I'm going to use some graph paper. So we're going to draw an x-axis and a y-axis. Weird sound. Should have probably done this before. Should maybe have lead. There we go. That's a little better. So there's our x and there's our y. So we're going to take our first vector. I am also a big fan of color, so I'm going to use colored pencils to keep these all straight. So jet 1. Jet 1 was at an angle of 76 degrees, and it had an energy of 82.2. So we want to draw these to scale. So we're going to come along and we're going to draw at 76 degrees. So right here, we're going to draw a line that is 82.2 giga-electron volts. So that's going to be, let's just say 8.82 there. So if we, 8.8 is right there. So we're going to go, that's our first vector. So this is jet 1, and I'll just label that one with that. So this is jet 1. So this is the angle of 76 degrees, and we had an energy of 82.2. Okay, so this is the first vector on our vector diagram. Then we had our muon going around in about the same direction. It was at 67 degrees and 34.4 giga-electron volts. So let's find our 67 degrees right in here. And that was quite a bit shorter. So 34.2 is going to be about 3.4. So if we line that up, we're going to go 1, 2, 3.4. So there is our muon vector. So this is our muon 1, and it had an energy of 34.2 and 67 degrees. Could put that 76 up here. Keep those straight. All right, so there's our second vector. Our second jet was at 135 degrees and 39.8. So let's find our 135 degrees. over here. Let's use orange maybe. So 135 is right about there. And so we're going to draw this. 1, 2, 3, right almost to there. So this is jet 2, at 135 degrees, and it was 39.8 giga-electron volts. All right, then we have our second muon was at 174 degrees. So 174 degrees is going to be right here. And it was, oh, actually that was our second muon. And it was 8.6. So if we line up that 8.6 right there, can't seem to line it up. There we go. Now line up that 8.6. Oops. So this is our muon 2. And it had an energy of 8.6 and an angle, what did I just do? 174. Alrighty. Then we had our other little jet that was 183 degrees. So right, 1, 2, 3, about there. And it was 18.8. Ooh, you know what? This is wrong. This is way wrong. This was 8.6 giga-electron volts. So that should actually end way, way, way over here. Way over here. That should actually be here, where this ends. I didn't scale that one. So let's, okay. It's right angle, just a bad picture. Okay. So this is 1.88. It's going to be really, really tiny. On this one. So right about there. So this is our jet 3. And it was 183 degrees and 18.8 giga-electron volts. And then our last one, we're going to be 302 degrees. So 122 is where this one was. 122 is going to be about right here. And it was 4.83. 48.3. So 4.83 is going to be our line right here. So this is jet 4 at 302 degrees and 48.3 giga-electron volts. All right, so that looks pretty good except for this little glitch right there. So those are our vectors. So this is our vector diagram. Now what we want to do is add all of these together. Now of course you could have added them all together as you went. That's just a different way to do it, is however you want to do that. But we still have to figure all of the x and the y components for these. And so remember, when we have all of these 2 dimensions, we're going to draw these x and y components. That's what we're really looking for. So for example, this muon right here is traveling not directly along the x and not directly on the y, but it's moving a little bit in the x direction and quite a bit there in the y direction. So it's going off in this direction right here. And so what we want to do is we want to find what is the magnitude of that y direction and what is the magnitude of that x direction. So we have a right triangle here, and we know that the hypothesis is equal to 34.2. And we also know that our angle is 67 degrees. So we can use that to find the components of each one of these vectors. And so in the case of our x direction, okay, our x direction is going to be adjacent to our angle. So our x is going to be our adjacent, which over our hypotenuse is going to be the cosine of our theta. Okay, so adjacent over hypotenuse is our cosine. So in order to find this adjacent value, what we're going to have is our x component is going to be equal to our hypotenuse times the cosine of our angle. Let's get rid of that so we're not confused. Not equal. There we go. Now for our y direction, our y is opposite. So in this case, the opposite is our y. And over hypotenuse, this is going to be our sine function. Okay, so our y is equal to the hypotenuse of our vector times the sine of our angle theta. So we're just going to do that for each one of them. So we're going to start here with our mu on 1. So the x component for our mu on 1 is the cosine, so the hypotenuse, which is 34.2, times the cosine of our angle, which was 67 degrees. And then we'll just get our little calculator here and take 67 times cosine times 34.2, and we're going to find the x component of this to be a positive 13.4. And then we're going to do the same thing with our y. We have 34.2, y is sine of our 67 degrees. So 67 sine times 34.2, and we're going to have a positive 31.5. We're going to do the same thing for jet 1. So our x is going to be 82.2 times the cosine of 76 degrees. So 76 cosine times 82.2. And we have a positive 19.9. Y is the sine of 76. And we have a positive 79.8. Our jet 2, we have an x of 39.8 with a cosine of 135. And this actually gives us a negative 28.1. And that makes sense because if we define this as our positive x, this is going in the negative x direction. So our y will be 39.8 times the sine of 135. And we have a positive 28.1. Our little muon over here, we have an x. Let's see, it's 8.6 times the cosine of 174. And our y is 8.6 times the sine of 174. Whoops. So we have negative 8.55. And then we have 174 sine times 8.6. And we have a positive little tiny number here, 0.899. Our jet 3 was 18.8 cosine of 183. Our y was 18.8 and sine of 183. So 183 cosine times 18.8. It's a negative 18.8 sine of 183. And we have a negative 0.984. And one more. We've got our jet 4. The x is 48.3 cosine of 302. And our y is 48.3 times the sine of 302. 48.3. So we have a positive 25.6, and then we have a negative 40, let's just say that 0.9, 40.9. All right, so now that we have all of our x and y components, we just need to add them all up. So we're just going to make a list over here. So for our x, we're going to have a positive 19.9. We have a negative 28.1, a negative 8.55, and a negative 18.8. And a negative, positive 25.6, I skipped one. Oh, and this one. So positive 13.4. All right, so we just add all of those up to find our total x component. So we have 19.9 minus 28.1 minus 8.55 minus 18.8 plus 25.6 plus 13.4. So what we get is a positive 3.45 as our x component of our resultant vector. So then we have our y, and our y is going to be positive 79.8, positive 28.1, positive 0.899, negative 0.984, negative 40.9, and positive 31.5. So we're going to add those up. So we have 79.8 plus 28.1 plus 0.899 minus 0.984 minus 40.9 plus 31.5. So that gives us a positive 96.617. So this is the y and the x coordinate of our resultant vector. And so we can see it's going to be a little bit this way and quite a bit up this way. So our resultant vector is going to be up in this area right here, which makes sense because this is where a lot of our, especially our big energies, are headed. So what we can do is, let's just draw a quick triangle just to keep that straight. So here's our resultant vector. Actually, it'd be up here, wouldn't it? So we're going to draw it. It's going to look like this. Okay. So this is going to be our resultant vector. So if our y and our x, we can find this using Pythagorean. So let's just square that. Plus 3.45 squared, square root. So this value is 96.7 giga-electron volts. We can find the angle theta by using tangent. So tangent of theta is opposite over adjacent. So our opposite is our x. So 3.45 over 96.617. So 3.45 divided by, and then tangent. So our theta, our angle, is 2.05 degrees, so pretty small angle. So we can actually draw this, right? We can come back over here and do we're looking at this angle right here. I didn't draw it from the x, I guess, did I? I did that kind of weird. So 2 right in there is where that resultant goes. And it has a magnitude of 96.7. Scooch that back just a little. 96.7, so right in there. Where's my line? So this is the resultant right here. So this is the sum of our energy. So now we have this resultant vector. Now remember, we are needing to have our momentum to be 0 before and after the collision. And this resultant represents the sum of all of the particles that we can detect. So our 4 jets of energy and our 2 muons are represented in this vector sum right here. So our missing particle, the neutrino, must have a magnitude that is the same as this vector sum. Okay? So the resultant vector that we found must be the same magnitude as the energy of our neutrino. It's just going to be in the opposite direction. So our neutrino is off over here at a 2-degree angle, so it's going to be right in there. If we line that up, we can just make that opposite, can't we? So this was 9.67. So if we draw our line this way to here. Okay, so this right here represents the energy of our neutrino. And you can kind of see this balances out a little bit better. So we didn't have much energy going this way. But now that we have this resultant vector, our neutrino must have a momentum that is the same magnitude as our resultant, but in the opposite direction. So our neutrino is going off in this direction with an energy of 96.7 giga-electron volts per 3. And at this angle, 2.05. Okay? So this means that the energy of our neutrino is 96.7 giga-electron volts. So there's one problem solved. We now have the missing energy from our neutrino. Now, in order to find the mass of the top quark, all we have to do is add all of our energies together. This is the total energy and mass of the system before, during, and after the collision. So since at one point during the event, we only had a top quark and an anti-top quark, and since both of those particles have the same mass, if we divide the total mass of the system by 2, then we can find the mass of the top quark. So really all we have to do is take all of these energies. So here's our energy of our muon. So we have our energy of 34.2. And we have an energy of 82.2. And an energy of 39.8. And an energy of 8.6. And an energy and an energy of 18.8 and an energy of 48.3. And now we also have the energy of our neutrino here. So we're just going to add all this up. And sorry about my fan, it's very loud. So our total energy is 328.6 giga-electron volts per C. So we'll see where you can get this. So we just take all of those energies, We added them up, and we got 328.6 giga-electron volts per C. Now, this is the total energy. This is also the total momentum. This is also the total mass. So if we take that total mass and we divide it by 2, then we're going to get the mass of our top quark to be 164.3 giga-electron volts per C. So that is how you find the mass of a top quark.